Next, I want to talk about some typical applications. By no means exhaustive, but applications that are important. Oil well drilling systems, stabilized platform, inertial guidance systems, strap down inertial guidance systems, submarine towed array. These are some examples of systems that, particularly the oil well and the towed array systems that my company is involved in. So this is a picture showing an oil well being drilled horizontally. Many years ago, oil wells were just drilled vertically. The technology to guide the drill bit in different directions wasn't developed until the 1990s. But nowadays, most wells are either horizontally drilled or directionally drilled, so that the wellbore is deviated. And the reason for this is to maximize the amount of oil or natural gas that are produced. And the instrument that had to be developed along with the means of changing the direction of the drilling is a sensor that we call the directional sensor. And the directional sensor uses 3/4 inch accelerometers and a 3-axis magnetometer to sense gravity, sense the pull of gravity, and the magnetometers sense the Earth's magnetic field. And so what this does is gives information on the inclination of the wellbore, the roll angle of the wellbore, and the azimuth angle of the wellbore. And this is what the directional driller on the surface needs to have to properly operate the system. And this is a very high accuracy system. The inclination accuracy of these systems is plus or minus 1/10 of a degree over the total temperature range, room temperature to 175. And that's where the 1 millig accuracy, these systems have to be 1 millig accuracy over the whole temperature range. And of course, this is an environment that's got a lot of vibration and shock. And so these sensors, these directional sensors, have to be rugged and high temperature capable. It's not unusual for a wellbore like this to be a mile deep and the length of it 2 miles. And in a situation where you're drilling through a producing sand that might be 10 feet thick, you've got to have really good directional control to stay within the stand and maximize the oil production. There are 2 types of inertial guidance systems generally in use. This depicts a stabilized platform guidance system. This is what used to be used on the Navy submarines. I was involved in that many years ago, but I'm not sure that it's relevant today. They probably are using the strap-down systems. But anyway, this shows the picture on the right shows the stabilized platform, and there are 3-axis gyro which measure the roll angle of the platform, and that roll angle that information is fed to 3 motors that stabilize actually 2 motors that stabilize the platform, so that the accelerometers, the 3-axis accelerometers that are placed on the platform, can measure acceleration, and that can be integrated to measure velocity, and integrated twice to measure the position change. And so this is the typical system. It's the older system, but it still works quite well. This is an interesting depiction of what was represented as a strap-down system. In a strap-down inertial guidance system, you don't use a stabilized platform, and it makes things simpler because the motors are sort of bulky, and so in a strap-down system, your gyros and your accelerometers are strapped down. They don't move with respect to each other, and the platform is not stabilized. And so, as this diagram illustrates, the algorithms to separate gravity and acceleration are complex, but that's what you're essentially doing. You're compensating for the fact that if you want to measure position, you don't want to measure gravity, and so you've got to remove that factor. I've talked about submarine towed arrays. This is a diagram of submarine towed arrays, and these are long tubes that are 3 or 4 inches in diameter, 5 inches in diameter, filled with electronics, filled mainly with sonar systems that we show, passive sonar systems. They're not active. They're listening for propeller noise. And this array could be several miles long. It could be a mile behind the submarine. And along the array, there are placed heading sensors. A heading sensor, we call it heading sensor because the main information that the submarine wants to know is what the azimuth angle of the array is. But the heading sensors have 3-axis accelerometer and 3-axis magnetometer, and so you get much more than just the azimuth angle. But the idea here is that once you hear sound from another submarine, for instance, you got to know the orientation of the array so you can tell where the noise is coming from. Now, this is an application, as I mentioned before, that there's not enough room there. The typical heading sensor that we manufacture is about 25 millimeters in diameter, and that has to have a pressure barrel to protect against the pressures. So the accelerometers that are typically used are MEMS high-end MEMS accelerometers, but an application for our smaller quartz hinge accelerometer would be to put it in these arrays. And the big advantage of that is, these arrays go out and they have to be out there for years before they come back in for repair calibration. And so, the accuracy over a period of time is of the utmost importance. And in fact, it can affect the calibration time when they have to bring the thing back in. And to bring these back in for calibration costs hundreds of thousands of dollars. Okay, to conclude, the points I want to emphasize are our quartz hinge accelerometer is high accuracy over time and temperature, and both of those are very important. We've included internal temperature calibration, so the systems are much easier to use. They're usable out of the box, and we provide analog and digital interfaces. And we actually provide a calibrated temperature calibrated analog output if that's required. And finally, the size, the miniature size, emphasizing the smallest one in particular, which is unique. Okay, well that concludes my presentations, and so if there are any questions,